We are going to continue to talk about hypothesis testing in this next lecture. Specifically, we're going to talk about testing the null hypothesis and the rest of the story. We started with a question. We were interested in whether the average number of minutes of vigorous exercise per week for people in the Deep South is lower or higher than the minimum exercise requirement for health benefits. And we know that the minimum exercise requirement for health benefits is 150 minutes with a standard deviation of 10 per week. And we turned that research question into a research hypothesis. Our hypothesis is that the average number of minutes of vigorous exercise for people in the Deep South is different from the minimum weekly number of minutes of exercise that are required for health benefits. And from the research hypothesis, we formed two statistical hypotheses. The alternative hypothesis, which corresponded to the research hypothesis and postulated that mu-r and mu-ds were different, and the null hypothesis, which was everything that the alternative hypothesis was not. The null hypothesis postulated that mu-r and mu-ds were exactly the same. We know that this is a non-directional hypothesis because the question has to do with differences. And we know that a non-directional hypothesis results in a two-tailed test. And now it's time for us to learn how to test that null hypothesis. We need to understand the workings of the process of null hypothesis testing first, though, because testing the null is a little complicated. We will learn how to choose from many test statistics eventually, but we will start this process of null hypothesis testing by using just one test statistic. We've already determined that we will be doing a two-tailed test as our hypotheses were non-directional. We need to talk about assumptions for the z distribution, which we will be using first, and we need to learn about alpha and decide on alpha and the size of the critical region. So we need to figure out which test statistic. We start with the null hypothesis, and the test statistic is determined by what information we already have with regard to that null, what information is needed, and what information is being requested. Let's look at the research question again. We can see that we don't know the average number of minutes of vigorous exercise for Deep South population, so we'll need to collect sample information to get that mean. We do know the minimum exercise requirement for health benefits and the standard deviation, and we can see that the researcher is asking for a range of means. A range statistic is requested, and the range statistic that we will learn about is the confidence interval. So we will need to learn about using confidence intervals to test this null hypothesis. There are three possible scenarios. If we know the population mean for the recommended number of minutes of moderate exercise for health benefits, and we do, and we know the Deep South population average as well, which we don't, we can just compare the two population means. If those means are the same, then the null hypothesis is true. If those means are different, then the null hypothesis is false, and we're done. No more calculations. Yeah, dream on. That almost never happens. If only one mu is known, but not both, just one, and sigma is known for one group, either group, then we have to find a sample mean, x bar, from the sample of the population that has no mu values. Our population that has no mu values are the Deep South population. We have to estimate mu from x bar, the sample mean that we collect from the Deep South, and we will assume that sigma is the same for all the groups. This happens, but it's rare. If sigma is not known and we only have one of the mu's, or we don't have any mu at all, then we need to estimate all that missing parameter information using sample information, and this is what happens most of the time. We need to obtain a sample and compute the sample mean on the Deep South number of minutes of moderate exercise values. And just remember that we do not expect that sample mean that we obtain to be exactly equal to the population mean for Deep South folks because of what? Sampling error. And here begins our hunt for mu, the Deep South mu. So we randomly sample from the population of Deep South participants. We have 9 participants in our study, so n equals 9, and the average number of minutes of moderate exercise is 57.77. We know that because of sampling error, that 57.77 is not supposed to equal 150. But is it so far away from 150, the mu for the other group, that we would not expect our mu to be 150? Or is it pretty close to 150 so that we would expect that mu of 150 even though our sample mean is only 57.77? We can't answer that without knowing how spread out our sample means are. Just chance spread, just nothing special but the spread of the sample means coming from 1 mu. We can't know that without computing sampling error. So how much variability do we expect in those sample means from the Deep South folks when we know the means are not equal to one another or to their own mu just by chance because they come from a sample? The central limit theorem says sigma over the square root of n, and for us that would be 10 over the square root of 9. So 3.33. Those sample means based on 9 scores from this population of Deep South folks should vary 3.33 minutes just by chance. We already had the population information for the recommended number of minutes of exercise for health benefits, and then we sampled 9 folks. We computed the sample mean for those folks, and then we computed the standard error. And what does that mean in our hunt for mu? Well, first, the sample mean that we just obtained, 57.77, is coming from that sampling distribution of the mean that has a mean exactly equal to the value, the mu we are looking for, the population mean for the Deep South folks, and a standard deviation of the means, or standard error, of 3.33. That 57.77 might be any one of those means in that sampling distribution of the mean. Most all of the scores, 95% of the scores, are between plus and minus z-scores of 1.96, and most means are between plus and minus z-critical values of 1.96. The sample mean that we just obtained, 57.77, is coming from that sampling distribution of the mean that has a mean exactly equal to the value we are looking for, the population mean for the Deep South folks. The CLT tells us that. The CLT also tells us that the distribution of means is normal or gets more and more normal as in the sample size increases. So most all of the means, 95%, are between plus and minus z critical values of 1.96. That 57.77, that might be any one of those sample means in that sampling distribution of the mean, but likely it is somewhere between those z critical values where 95% of the means are located. Just like most scores, most all the scores in the population distribution of scores, 95% of the scores are between z-scores of plus and minus 1.96. So too are most means. Most all of the means in the sampling distribution of the mean, 95% of the means are between z-critical values of plus and minus 1.96. Our mean is just one of those sample means, and we don't know which. What we do know is that the sample mean we obtain likely comes from the 95% area of the sampling distribution of the mean, because 95% of those means are located there. We can think this through and conclude that when we surround our sample mean and also 95% of the other means like our sample mean, we will almost always, 95% of the time, surround the population mean we are hunting. And this process produces a range of means that likely falls about our missing population mean, just like the researcher requested. And now we know that mu for the Deep South folks is likely somewhere between 51.3 and 64.3 minutes of exercise per week. Our researcher asked for an interval estimate of the parameter for the Deep South folks. We gave her one. The population of Deep South folks likely averaged somewhere between 51.3 and 64.3 minutes of moderate exercise. We will talk about point estimates later, and we still have to test the null hypothesis. This was just all the preliminary work. And we have just computed our first interval estimate, a confidence interval. A confidence interval is a range of values formed in such a way so that if infinitely many ranges are formed just in that way, there's a set probability that ranges so constructed will fall about the parameter of interest. A confidence interval about a sample mean is a range of sample means formed in such a way so that if infinitely many ranges are formed about sample means, there's a set probability that ranges constructed like that will fall about the mu that produced that sample mean. Remember, we went fishing for mu for the Deep South folks. We had some evidence of the location. X bar gave us that information, the sample mean. And then we formed an interval around the sample mean with a lower and upper mean that likely surrounded the mu, the population mean we were hunting. A 95% confidence interval about the sample mean is a range of sample means formed about an obtained sample mean in such a way that if all possible sample sizes of n were drawn from the population of scores and all possible 95% confidence intervals were formed about all the possible sample means computed from those scores, 95% of those confidence intervals would fall about the mu that produced the sample mean and 5% would not. When we form a 95% confidence interval about the sample mean, 95% of the time our net will fall about the population mean, mu, that we are hunting. And 5% of the time our net will miss the mu entirely. We can split up the area around our X bar where we cast our net into two regions, the region of non-rejection and the region of rejection. When the mu for the other group, the recommended minutes of exercise for our scenario, is located in the area beyond our confidence interval, in the region of rejection, in the critical region, then we reject the null hypothesis that our two mu's are the same. And that is a significant difference. When the mu for the other group, the recommended minutes of exercise for our scenario, is located in the area between, in the region of non-rejection, then we fail to reject the null hypothesis that our two mu's are the same. And that is a non-significant difference. So here it is more formally. We formed an interval around X bar, the sample mean for the group of Deep South folks. We found lower and upper sample means that corresponded to plus and minus 1.96 standard errors around the sample mean that we found a 57.77 from our Deep South folks. We know that this is a two-tail test, so we placed our critical regions, half of alpha on one side and half on the other, in both tails. So when we decide on the width of the critical region, the region of rejection, the area beyond the interval, the size of that area is called alpha. And we only have two choices for alpha, 0.05 or 0.01. With alpha 0.05, 5% of the distribution around X bar is devoted to the critical region, and that 5% can be on one side only or split between two sides like we've done. With alpha 0.01, only 1% of the distribution of means around X bar is devoted to the critical region. For reasons that we will talk about later, most people set alpha to 0.05 most of the time, so we will use alpha 0.05. Alpha is always written as a proportion, and the confidence interval is always written as a percentage, not my doing. And remember that we got those Z critical values from the Z table. We want for 95% of the distribution of means to be between plus and minus Z critical values. So if 95% of the distribution is between and 2.5% is beyond on one side, we add those values together to get the 97.5% in the body. And the Z value that corresponds to 0.975 in the body is 1.96. And when we use that sample mean as an area to focus on, when we cast our net, if we cast our net very wide, covering 95% of the sample means around our obtained sample mean, if we cast the net between plus and minus 1.96 Z critical values associated with our sample mean, then we have an awesome chance of surrounding the mu for deep south folks, the mu that we are hunting. Remember that we can't cast our net over the entire distribution of sample means because they are like the ocean, infinite in size, so we have to focus our search. So we focus our search around the obtained X bar, around the obtained sample mean, and that's a good estimate of mu for the deep south folks. And we know from the Z-score table that most all the scores are between Z-scores of plus and minus 1.96. That covers 95% of the scores. And we called anything outside of that an outlier. So in the sampling distribution of the mean, most all the means are also between Z critical values of plus and minus 1.96. And we are assuming that the population distribution is normal, so that for sure the sampling distribution of the means is normal. And we are assuming that we have randomly selected these scores so that there is no bias in those means in the sampling distribution of the mean. And we are assuming that the scores are independent so that there isn't a globbing up of scores together because they are related, like family members who exercise together, giving us the same scores because they only ever exercise together and all their scores are the same. And now we know the recommended average and standard deviation. We have an estimate, X bar for the deep south average, and we know the standard error, how variable those deep south means should be by chance. So now we know what the spread of the means would probably look like if the null hypothesis was true. We would get a sample mean from the deep south folks that is no more than 1.96 standard errors away from the mu for the recommended exercise minutes per week. That would be what is expected for sampling error. Anything beyond plus or minus 1.96 standard errors is very likely a real population mean difference. And we, from our testing of the null hypothesis, can form this conclusion. Deep south folks engage in moderate exercise for significantly fewer minutes than is recommended. The only difference for a one-tailed test is that the Z critical value changes. We are looking in only one direction. So we form the interval around X bar, and then whichever way we are looking for the other group mean, we cut in that direction. The critical value from the table, with 95% of the means in the body and 5% located all in one tail, is 1.65. It is a positive 1.65 because we're looking to the right of the sample mean to reject the null hypothesis. When we use the Z distribution, we assume that we sampled the scores in a random sampling way, that the scores in the population are independent of one another, that the scores are normally distributed in the population, that the population variances are exactly the same for all groups. That's called homoscedasticity or homogeneity of variance, and that sigma is known. So what do you think? The computations are easy, the concepts are hard. And so is life. Signing up for classes is easy, making good grades, understanding the material, that's work. But everybody knows that everything is difficult before it gets easy. So let's recall how it works. We started with a question. From that question, we formed a research hypothesis. From that research hypothesis, we formed two statistical hypotheses, the null and the alternative. We tested the null, we rejected the null, and our conclusion was that there's a significant difference. We used the process of confidence intervals to form an interval around x bar, our sample mean, that fell also about most of the means from the population of means for the Deep South folks, and determine whether our mu from the other group, the recommendation, was in the region of rejection or region of non-rejection. And we found that it was in the region of rejection. That's how we rejected the null in favor of the alternative. So we rejected the null hypothesis, but we can't say that we accept the alternative hypothesis just because we reject the null, because we didn't test the alternative hypothesis. So our conclusions can't be about the alternative hypothesis. And we can't say that we accept the null even when we fail to reject the null, because we do have some evidence of a difference between population means when mu does not equal x bar, the sample mean. We just don't have enough evidence to reject the null. Even when we get a significant difference, it doesn't mean that we have a meaningful difference. We will get a significant difference between men and women on perceptual IQ. Men have a higher perceptual IQ, and women have a higher verbal IQ. But that difference is so small that it doesn't make any difference at all in the real world. It's not a meaningful difference. We almost always want a significant difference, and interpreting a non-significant difference is difficult. It could be that no differences exist between population means, and that would lead to a non-significant difference. But it could be instead that we ran a sloppy study, or there was too much variability within groups to notice between group differences, or the differences were too small to notice with the sample size we had. There are lots of reasons for finding no significant differences. Sometimes, rarely, we want for there to be no significant differences. If we want no significant differences, one way to build a case for there being no differences and not just having a sloppy study is to include variables that you know because of prior literature will have significant group differences and have a large enough sample size to detect even small differences. We will talk about that later. In that way, though, you will find some significant differences, maybe just not the ones you're focused on, and the sloppy study or small n argument for no significant differences is not valid. So we work the steps. And next up, we're going to test the null hypothesis with z-tests and t-tests.